Alright y'all, this is Mr. Gibson again. I'm going to take you guys through a quick review of calculating probability. Now, what I'm going to take you guys through is a few circumstances here where you're going to have different formulas for calculating probability. First is if we have two events together, so an and problem, and there's two circumstances or events that happen like A and B. Okay. If the events are independent, meaning they have nothing to do with each other, they won't affect each other, so that the probability of one event happening won't affect the probability of the other event, and we call those independent. And if we're going to calculate the probability of both of those happening together, A and B, we take the probability of event A times the probability of event B to get the probability of event A and B occurring together. Now, if the events are dependent, meaning the probability of one event happening is dependent on the other event happening, then we have just a slightly different formula. We have what we call conditional probability in this. It's expressed with this right here. So if we want to find the probability of A and B, we multiply the probability of A times the probability of B given A. This little line means given. Given as in, okay, A happened, what's the probability of B? Okay, we'll see some examples to clarify this. The other thing that we're going to look at is combining events together. Okay, the probability of two events combining together. So there's two circumstances here where we're going to have a mutually exclusive circumstance where A and B, the two events, don't overlap at all. They have nothing to do with each other. Okay, so if I want to find the combining events, or saying probability of A or B happening equals the probability of A plus the probability of B, simply. Okay. Then the other circumstance is if it's inclusive, meaning A and B, there's some overlap. There's some times that A and B are the same thing. So what you do here to find the probability of A or B, you take the probability of A, add it to the probability of B, but we have a double counting problem, right? If we've taken all this A and all this B, there's some overlap there that we need to get rid of. So to get rid of that overlap, we subtract off the probability of A and B, the probability that A and B are where probability of A and B are the same. Okay. Anyway, we'll see some examples to give us a little more clarity on this. So, first one, what is the probability of rolling a 5 and a 3 on a 6-sided die? Okay. These events are independent. If I throw a 5, it will not affect whether or not I'll throw a 3. I'll roll a 3 on the next time, okay? Whatever I roll the first time won't affect the probability the second time, okay? So these are independent events. So I'm going to take the probability of, I'm going to say 5 and a 3, okay? So that means I need to take the probability of rolling a 5 times the probability of rolling a 3, okay? I might want to write rolling a 5 or rolling a 3, but I think this gets the idea across. On a 6-sided die, probability of rolling a 5, well, there's one side that's a 5 out of 6 sides. Probability of rolling a 3, well, there's only one side that's a 3 out of 6 sides. So the probability of rolling a 5 and a 3, we're just going to multiply those together, and I'm going to get 1 times 1, okay, 6 times 6, 36. So 1 in 36 chance. Okay, 1 in 36 chance. So that's what the independent event. Okay. Now, next example. In a 52 deck of cards, what is the probability of drawing a 10 and then a face card without replacing? So we're going to draw. So what's the probability of me drawing a 10, not putting the 10 back in the deck, and then drawing a face card? So drawing a king, queen, jack or king, or jack, king, queen, or ace. Okay, let's call those face cards. I'll include ace in this. Okay, these are dependent events, meaning when I draw the 10, there'll be fewer cards in the deck. So drawing a 10 has affected the probability of drawing a face card. Okay, so probability of 10. I'm just going to put an F for face, okay? So that means I want to calculate the probability of drawing a 10 times the probability of drawing a face given I drew a 10. Okay? So the probability of drawing a 10, pretty simple. There are 4 10s in a deck out of 52 cards. Okay? Alright, straightforward right there. Alright, now, face cards. There are 4 face cards per there are 4 face cards per suit. So hearts, hearts, spades, diamonds, and spades, diamonds, and clovers, or clubs, that is. So face given 10. Now this is where I want to explain dependent events here, okay? So there are 16 face cards, if I include aces. No, I'm not including aces, my bad. No, I am including aces, my bad. Including aces, there's 16, because there's 4 per suit. Now here's where we have the dependent part. We no longer have 52 cards in the deck. We have 51. We have 51, okay? So what you would do at this point is you take 4 times 16 over 52 times 51, okay? Whatever you got there, you would just go from there. Just for the sake of time, I don't have my calculator out. I'm not going to multiply that unless I have a calculator around here. No, we're good, okay? So again, you just multiply across. The big thing here is dependent. See this number on the bottom, it's no longer 52, it's 51 because we drew a card. So that's when you have a dependent event. Okay, let's talk about combining combining probabilities together. Well, this case, I'm going to have a 52 deck of cards. What is the probability of drawing a 2 or an ace? Okay, these are mutually exclusive because what that means is they have nothing in common. There's no 2 that can be an ace. No ace that can be a 2. They're just both by themselves. Okay, so probability of 2, or I'm going to put an A for ace. Okay, so I'm going to multiply. I have the probability of 2 plus the probability of ace. Okay, probability of drawing 2. Well, there's 4 2s out of 52, and plus 4 aces out of 52. Okay, add those together. They have the same common denominator, so I don't need to do anything to the denominator. All right, so it's going to be 52 on the bottom. 4 plus 4 is 8, and then let's see, that would reduce down to, I think, 4/26. That would reduce down to 2/13. Okay, so I just added those together and I just reduced down from there. Okay, so they aren't, so if it's a case where you're combining probabilities, probability of 2s and probabilities of aces, or the probabilities of aces, you just add them together. Okay, mutually exclusive, meaning there's no 2s or aces that are the same. So if you're a little confused about mutually exclusive, let's look at another example where we have an inclusive case. Okay, again, we're going to go with the deck of cards. What's the probability of drawing a jack or a heart? Okay, again, I'm just going to set this up as J, or I'll make a little heart symbol, I guess. It's not a very nice one. Y'all can make fun of me. Okay, make that look a little nicer. Alright, a jack or a heart. Okay, so probability of jacks plus the probability of hearts. Okay, now let me just start this off. Okay, there are 4 jacks out of 52 cards. Okay, there are 26 hearts. No, 13 hearts, my bad. Oops. 13 hearts, because there's 3 suits, it's 1 suit is a heart. So 13 hearts out of 52 total cards. Now here's the thing. If I were to add those together, I would double count. because there's one jack that's also a heart. Okay? So I've counted the jack here, and then I've also counted one of these cards as a heart, and it's a jack as well. So what I'm going to do is I'm going to subtract off 1 over 52, because one of the cards is both a jack and a heart. Okay? So then, all the same, they all have the same common denominator, so I can combine them together. This would be 17 minus 1 is 16 out of 52. Okay. We can reduce that down again. I think this would be about 4/13, I think. Yeah, it'd be 4/13. Okay. So those are some problems and some stuff about probability. Good luck on your EOC.